together on projects, multimodal artifacts that they designed and developed, field observation notes, and formal and informal interviews with youth. And I examined this data to ask, what role did the youth's artistic vision and process play in their learning? Today, I will briefly share 2 projects that were developed by youth in this Fab Lab. My goal is to reflect on the role that art and aesthetic played in learning. And the larger point I will make is that the synergies and tensions between the youth's artistic vision, their message or what they wanted to convey through their artifact, and techniques helped to drive learning. I'll start by talking about the Black Lives Matter kinetic sculpture. Nasir was a self-identified maker and worked as a lab steward in this lab. He was a high school senior and had been a part of this community for about 5 years. The idea for the Black Lives Matter kinetic sculpture originated in his school art class, where his teacher asked students to examine art of the civil rights movement. Their teacher asked also if they wanted to work on a project for Black History Month. Nasir decided to create a piece that would express his views about the Black Lives Matter movement in relation to the argument that the movement should be focused on all lives matter. Here is his idea in his own words.
Basically, I wanted to challenge the idea of all lives matters versus Black Lives Matters, and I wanted to show that all lives can't matter until Black Lives Matter or those who are going to get represented matter. So I had this idea of having a gear surrounded by 4 equal gears, or here, let me show you this one. And I have a video of it moving, but we're going to avoid all that scary stuff. Basically, the idea was that they all revolve around that center gear there, and to show that this is like all lives mattering. And you take out one gear, and then the project will stop working. I haven't figured out how to do that yet, but that's what I want to do. And so it won't. You take out one gear, it's just stop working, and it won't work until you put it all back in. And then
You can go to the. These are some of the initial sketches Nasir made. His design of this sculpture was a set of planetary gears as a closed system in which each gear represents different ethnic and racial communities. He describes that when one of the gears is removed, the rest of the gears do not function, hence representing the interdependence of communities and the importance of each in the functioning of the whole. Nasir designed the first few prototypes of this sculpture in Inkscape. It's not clear which material his first prototype was of, but some of the images we have are of Lexan sheets and wood. He talked about his process as eyeing it. He said, at some point, I kind of gave up on just picking the right numbers and I just eyed it. So like I made sure as long as this is in the center and it was touching all 4 of these gears, I was okay. When he tested the first few prototypes, he encountered a problem.
I put them all in hoping they would work, and they were like pushing together too tightly, and they would like pop out when I would spin it. So, yeah.
The gears in his prototype pushed together too tightly and would pop out when he tried spinning it. The gears not popping and not running smoothly was not in line with Nasir's aesthetic vision for his project. He wanted the gears to work smoothly. This specific aesthetic was tied to his sense of the fluidity and interdependence of communities that each gear represented, which was his message. His subsequent investigations into the project centered around trying to fix this issue. He speculated that eyeing it might not have worked, and let's see what he does next. Over the next 4 months, Nasir repeatedly revisited his project. His first approach was to try to measure each of the gears and be more precise with those measurements so they fit better. And that's the first image you see to the left there. When that didn't work, he consulted with a mentor from the same community, Derek, who was an undergraduate with an engineering major. Derek recommended using SolidWorks, which is a much more sophisticated, powerful, and complex tool. As you can see here, Nasir's first approach in using SolidWorks was to make a circle and add triangles around it to create a gear. Derek pointed him to tutorials on YouTube that led Nasir to start thinking about the gear as a collection of splines starting from the center of the circle. In my last interview with Nasir, and you can hit, yep. In my last interview with Nasir before he headed to college, he talked to me about what he called angle pressure as the gap between the teeth, which was important so the gears could move. And that was the reason why the teeth can't be triangular, because as he described, they would get stuck. In that same interview, Nasir also described to me how he continued to envision what the project would look like, whether and how the piece would fall out, what trade-offs he would be willing to make to execute his vision, where it would be displayed against a wall in the school or somewhere else. He ended the interview saying, "It's more I'm thinking a bit more of the end product, but I would not say I'm thinking about making it." Though Nasir's project originated in school, he was not required by his teacher to continue working on it. He did it because he wanted to, over 4 months. What I want to highlight here is that his sustained investigations and this process into making this sculpture work smoothly were driven by a tension or a lack of alignment between his artistic vision and techniques, or the tools, the technologies, the materials, and his own knowledge of gears that were in tension with his artistic vision. And this tension drove his learning. It kept him going, both as an engineer and as an artist. The other project I'll briefly allude to is the Waterworks project built by another group in the same community. The Waterworks exhibit was envisioned as a musical water fountain that changes color when different jumbo piano keys are pressed. This screenshot taken from their blog describes the project in their own words. They wanted to create a way for children to interact with music and water in public parks. Their message or purpose was in response to the problem of access and lack of engagement with music in their community. To build this exhibit over 6 weeks, Gus, Trissa, Sia, and Tyler went from being complete newbies in a fab lab to learning to design press-fit acrylic containers, writing code to play notes of a piano and light up an LED strip, and putting together a fairly complex project. And here again, just like Nasir, the learning happened because of specific synergies and tensions that they encountered between their artistic vision, which in this case was to design a playful experience with water, lights, and music for young children, the message or the work that they wanted their art to do, which in this case was to bring music into everyday spaces, and the specific tools, technologies, and materials that they encountered along the way. These synergies and tensions provided a fertile space for learning for these youth. And so as the Synergy 2 initiative launches Synergy Experiment, an experiment in K-12 education to create curriculum that focuses on the process of exploration, experimentation, and integration of scientific and artist tools, I look forward to seeing how these synergies and tensions surface in the work that takes place in K-12 classrooms. And the event today, below the surface, is an experiment in its own right in communication using art as a common language. This idea of using art to communicate science resonates with another project that I'm just starting out on that I will briefly describe. The project is called Choreographing Science, Youth Scientists and Choreographers Co-Constructing Meaning Through Choreography and Agent-Based Modeling. It builds on existing learning research on how embodiment and representing science through movement and dance can be a productive form of expression and learning for youth. It also builds on outreach programs such as Dance Your PhD, which is a contest that challenges scientists to explain their research without using jargon or PowerPoint or words, just using dance. The purpose of the contest is to educate by explaining complex theories through interpretive dance. It started in 2008 and it's still going strong. And so this NSF project aims to develop collaborative partnerships among youth, scientists, and choreographers to engage in scientific inquiry together by utilizing complex systems and choreographic modeling, and create performances that communicate scientific learning to the public. Our key goals for youth are that they come to see science as not settled and as something that they can contribute to and communicate to others. For scientists, our goals are for them to see complex systems, choreography, and youth's perspectives as generative to their own research, and to develop an ability to communicate their research to new audiences. While in the ethnographic study that I described before, I was a witness to what was going on. Here, my goal is to design an experience for participating youth and scientists so that they can benefit from the synergies and tensions that will result between dance and science. We are in the process of actively recruiting scientists for this program. So if you're interested or have questions, please reach out to me. And as I wrap up my talk here, I once again welcome you to Below the Surface. And I want to say this year's scientist-artist collaborators are about to share very shortly their wonderful creations. And when I look at this collection of work, I see the art as both amplifying the science, while at the same time, distilling it down into a diverse set of remarkably aesthetic art. I'm excited to learn more about the synergies and tensions that arose through these scientist-artist collaborations. So with that, I'll say thank you and welcome any questions that you might have.
Thank you for that wonderful talk, Dr. Wagh. Again, if you want to ask a question, you can drop the question into the Q&A box and we will read them out loud. So to start us off, we have actually a pretty hard question for you from Joan L. And she wants to know, if arts are such catalysts, why are they outliers to STEM when they could be integral as STEAM? And for those of you who don't know that acronym, STEM is science, technology, engineering, and mathematics, and STEAM adds the arts to that.
That is such an interesting, and you're right, Jen, difficult question. I am actually currently sort of trying to read into the history of when this sort of bifurcation happened, where science and art both not only became siloed, but also sort of acquired this, this different status. So just today I was meeting with choreographers on the NSF project I just talked about, and we were just talking about how kids see science and dance. And the choreographers were expressing that they themselves feel, they use the word inferior to scientists because they felt like dance is not as valued or sought after set of skills as science is. And so I don't have an answer for you at the moment, but it's something I'm reading into and I'm super curious about. But I will say that when you bring them together, it is super powerful. And I see that in my work all the time.
Chrissy would like to know, in your work, how do you adjust your methods to different age groups of students?
That's a great question. So I do a lot of, before I set out to do my studies, I will work very closely with the participants that I am working with. That might be in the form of interviews that I conduct with the group of people that I'm about to work with, or it might be I'll just go and hang out in their classroom or in the after school program that I'm going to be a part of, with the goal of just trying to understand what are the things that these kids know already about the topics that I'm bringing to them. Because the idea in designing experiences for them is to build on what they know, because that's the most powerful form of learning, when you can connect what's new to what you already know.
Perfect. And Jonathan would like to know, what has been the most important takeaway that has affected you personally that you've gained from this?
That's a great question. I think for me, it has something to do with connecting what you are bringing into classrooms to kids' own experiences outside of the classroom, because it's very easy to think of what we teach in classrooms and what's in the standards and what's in the curriculum as being important and as being the most important thing we want to focus on. But really, when you're able to tie that as an educator and researcher, when you're able to tie that back to kids' everyday lives and the things that they do outside of the classroom, is when the most powerful learning happens, because then kids see connections between what they're doing in school and the life they're seeing outside. And so what they see seems relevant to them.
Thanks for that answer. And again, if you have any questions, feel free to drop them into the Q&A box. Ruth would like to know, what's the challenge that you have in getting your research content out to the mainstream in an understandable way?
This is something that I'm actively working on. So when I publish my work or when I go to speak at conferences, I make a very conscious decision to speak at conferences that are academic, that are attended by faculty members or other academicians, but then also to go to conferences that are meant for educators, that are attended by K-12 teachers or education museum curators or after school program educators. And so the idea is to both present to audiences that are in the field and actively doing work, but then also to present to people in academia, because both the conversations that are happening into those two groups kind of inform each other in really interesting ways. And so it's important to be present in both those communities.
Great, thank you. And I think for one last question, obviously your work is also a collaborative process. Could you talk about kind of the people that you work with to develop your curriculum?
Yeah, so the groups that I work with are also very interdisciplinary. So the project, the NSF project I just talked about, we are a group of 7 women. Two of us are scientists. We have 1 engineer in the group. 4 of us are educators, and some people are more than one thing, which is why the numbers might not add up. 4 of us are educators. All of us see ourselves as researchers, and we have 2 choreographers in the team. And what I've found in my work is that when you bring interdisciplinary groups together, there's just, again, synergies and tensions. There's just more interesting stuff that happens because everyone's bringing very different language, epistemological understandings about the work, goals. And so it works really well when there are people from a diverse set of backgrounds coming together.
All right, thank you so much. That's our last question. I think that was a perfect question to end on so that we can move forward and look at the interesting ways that artists and scientists in this program have worked together. So with that, I would like to give a virtual round of applause to Dr. Wagh, and I will hand it off to Ellen.
Sorry, I had to unmute. Okay, thank you, Jennifer. So I'm about to introduce to you the 10 to 11 teams that we have, artists and scientists teams. I'll introduce you by who they are and let you know the title of their project. And then they will have a presentation for each of you. Jennifer Kenyon, who is a PhD candidate in the MIT WHOI joint program in marine chemistry and geochemistry, was paired with Lori Kaplowitz. Lori is an artist and Chancellor Professor of Fine Arts at the University of Massachusetts, Dartmouth. And their project is entitled Pursuit and Decay. They're going to tell you a little bit about that now. We may be having some technical difficulties getting their video up. So in the meantime, we could move to the next team. Oh, here we go.
You guys can all see it?
Yes.
Hi, I'm Laurie Kaplowitz, the artist.
And I'm Jennifer Kenyon, the scientist.
Tonight we are showing you images from our graphic storybook, Pursuit and Decay, which follows the journey of carbon in the ocean. As we turn the pages, we'll highlight salient features for you and talk about the science, the art, and our collaboration. How did we decide on this particular form to embody the science? At the time we met, I was working on an installation in the form of a 3D graphic novel, and Jen is a huge graphic novel fan. A storybook seemed like a perfect vehicle to address our interests and excite our respective artistic and scientific minds. One of the first challenges was telling the story of the science in 10 pages with precision and clarity. We had as a goal creating an educational tool for young students. Another challenge was transforming very non-visual, natural forces, elements, and processes into characters in a story. We did this by personifying them. Here, carbon is seen early on as toddlers playing a shadow game. Carbon, now a juggler, cycles on endlessly tossing his atoms round and round through the atmosphere, while the ocean, personified as a sleeping woman, breathes these atoms in and out. This is to represent the movement of carbon through our environment and acknowledges the ocean's role in buffering the effect of atmospheric carbon dioxide and subsequently climate change.
A common theme throughout this work is to try and see the unseeable, not only through the common motif of the carbon atom, but also here through large images of phytoplankton. These otherwise microscopic organisms are an art form in and of themselves. These images were painted from reference photos. The message we wanted to convey through our story was to teach people how scientists use radioactive elements to trace or follow carbon's journey as it goes from the atmosphere to the deep ocean. Radioactivity can be a difficult concept to digest, but Laurie managed to do a great job of showing how these tools can help chip away at the mysteries of the deep ocean. By using clever math, we can use radioactive elements such as thorium and uranium to give us an understanding of the rate or how much time it takes for carbon to move from the surface to the deep ocean. Laurie had me scan her copies of my handwritten notes in a laboratory notebook, and she incorporated these documents directly into her work.
Our story is written in the first-person voice, as told by the scientist. Everything is seen through her eyes, such as the panoply of nature and the binocular lens on the first page. But the reader only ever sees her hands. She's taking notes and examining specimens under a microscope. There are many recurring motifs that appear in the book. Circles and spheres are seen again and again, as well as hands. We see the scientist's hands at work, radioactivity's mechanical hands releasing energy, and carbon's hands juggling. This is not an art form or imagery I ever would have engaged in had it not been for this project. The collaboration with a scientist has allowed me to stretch my imagination and engage in making something entirely new.
And thinking about my science in this creative capacity has allowed me to better communicate my science in other avenues of my life. This work would also not be possible without the help of our graphic designer, Jonathan LaRue. Thanks.
Thank you, Laurie and Jennifer. Excellent. Now I have the pleasure of introducing Dr. Chrissy Hernandez, who is a graduate of the MIT HUI program. She's currently a postdoc and a postdoctoral associate at Cornell. And her partner artist is Kathy Hodge. The title of their project is Drifters.
Hi, thanks. You can go to the next slide. So hi, I'm Chrissy. I'm an ecologist interested in the population dynamics of harvested species. In particular, I'm captivated by tunas and their larvae. Bluefin tuna hatch at about 3 millimeters in length and over a few decades grow to be bigger than a human. They're powerful swimmers, able to cross the entire ocean within a few months. Historically, scientists have believed that Atlantic bluefin tuna spawn in only 2 regions, the Gulf of Mexico and the Mediterranean Sea. However, my work is helping to shed light on a 3rd region where spawning occurs, called the Slope Sea. Shown on this map at the bottom here as a green wedge, the slope C extends from North Carolina into the central Atlantic and is bounded by the shelf break where the ocean is 200 meters deep and the Gulf Stream. This dynamic region of ocean has many similarities with the other known spawning grounds, so it's not entirely surprising that tuna might spawn there. Next slide, please. So in my work, I collect plankton samples by dragging nets through the water from research vessels far offshore. Here I'm showing you a map of these locations and the locations in the slope C where we collected Atlantic bluefin tuna larvae in 2016. I'm also showing you a photo of an otolith, this image in orange. That's taken under really high magnification. Otoliths are made of calcium carbonate and are smaller than a grain of sand, and they're the inner ear of the larva. They grow with the larva to enable them to hear and balance, but their growth occurs in these daily bands like tree rings, which enable me to age the larvae. These otoliths are both an important tool for me as a scientist and aesthetically pleasing. I really love this study that Kathy made of a bluefin tuna larva and an otolith, because it shows the delicate details and symmetry of these tiny creatures and their even tinier otoliths. It's both informative and beautiful.
Due to the pandemic and distance, Chrissy and I have never met in person, but over Zoom, she named some things that sparked my imagination. The otolith, the slope C, warm core rings, and that larval tuna are plankton until they've grown enough to swim against the current. Next slide. I wasn't able to see larval tuna in real life, but could I see plankton? I bought a microscope, collected seawater near my home, and there they were. Next slide. I was in Maine when Chrissy texted me about the bluefin bonanza in South Portland, which gave me a rare chance to see a real bluefin tuna on the outside and inside. Next slide. This resulted in a plan for a large 3-panel painting. Next. The left panel depicts the research area of the slope C, the Gulf Stream, and the warm core rings that the tuna follow into the depths to feed. The middle panel shows the teeming zooplankton, phytoplankton, and larval fish. In the center is a bluefin tuna larva surrounded by a carbon atom. Plankton absorb carbon, much of which sinks to the ocean floor. In the daytime sky, the oxygen produced by the phytoplankton rises. In the right panel, the night sky holds the constellations that were present when Chrissy was at sea. The moon shines over the nightly plankton migration to the surface. Far below in the seamounts, magical and unknown sea creatures live. Next slide. I will place magnifying lenses in the spots where Chrissy found tuna larvae. Next slide. And perhaps the star of the piece under the big lens is a tiny days-old tuna larva that Chrissy found in her plankton net in the slope C, amongst many others. Research like Chrissy's will add to the knowledge of these magnificent kings of the sea. Thank you.
Thank you, Kathy and Chrissy. This was an excellent presentation. Now I'd like to introduce our next team, Max Jans, who's a PhD candidate in chemical oceanography in the joint program in the Department of Marine Chemistry and Geochemistry, and Sabra Malik, who is an artist and an independent arts and crafts professional. The title of their project is Forms of Every Breath You Take.
Science at its best, I believe, serves to celebrate, protect, and understand the life of this planet in its many forms. Is my partner Sabra here?
Art at its best, I believe, serves to illuminate and enrich our lives. Practitioners in both disciplines are equally passionate about and dedicated to the process of providing information, solutions, and a vision for betterment at large. As science and art collaborators, we see the world and a particular subject matter with a different eye, with the curiosity to continuously ask all the how, where, what, if, and why questions.
Sabra's artistic passion and my own scientific passion are ignited by a similar philosophy, the beauty of form. And here, as you can see, life in the ocean comes in many varied, ethereal, and beautiful forms. These organisms are called plankton, and the light harvesting photosynthetic plankton that are in our oceans power the planet.
I was blown away to discover these tiny creatures are responsible for creating about 70% of the oxygen we breathe, more than the land plants, perhaps, as the graph shows. And I thought to myself, why do so few people know this? I wanted to use my art to excite more people to embrace these unsung superheroes.
The biggest challenge in communicating my microscopic science is these creatures are invisible to your normal life. Consider zooming in on a human hair so far until it's magnified that we can see every ridge. That's what you're seeing on the left.
Yet, as you can see on the right, a phytoplankton, one of those plant-like planktons that allow us to breathe, next to this magnificent human hair seems dwarfed in comparison. These creatures are smaller than the width of a human hair, and yet they support all life as we know it. They are the foundation of the food chain, working all the way up to us.
And plankton come in many different forms. The study of living forms and structures is called morphology. And the morphology of plankton in the ocean has been intensely studied for over a century and is still being explored by science today. We hope that more people can recognize the importance of studying the microbial life in the ocean. Next slide, please.
Since this project began, I've begun to better understand the significance of life of these unseen heroes. The rhythm of waves is indeed beautiful, but tells us little about life beneath or the science behind it. Max and I explored these waters and these creatures together. As our collaboration progressed, I understood the role of photosynthesis in the life of phytoplankton and the importance of sunlight in the process of oxygen production by these microbial aqua dwellers. I realized why my hands always felt greasy after washing shrimp, for the bodies of plankton are lipids, body fats, that are a result of photosynthesis.
And Sabra has allowed me to join her in the beautiful process of textile work. We started our collaboration with a common appreciation for fiber art, especially Nick Cave, and an interest in light, both in its physical state as well as an enhancement element for performance or art.
My interpretation of Max's research is based on the morphology of phytoplankton. I start by molding textiles and finding ways for them to harness ultraviolet light. By shaping, coloring, and arranging them, I try to capture the unique forms of these plankton so that others too can visualize their beauty.
And we'll let the work speak for itself. We'd like to show you some of these molded forms of fabric and the plankton they depict.
Thank you, Max and Sabra. Fascinating, very beautiful work.
I needed to add something, Ellen, which is I hope this visual interpretation would excite you and others to embrace these unseen microscopic beings as the unsung superheroes of the deep, heroes that help generate around 70% of the world's oxygen and hence half or more of every breath we take. I hope this work will teach a rising generation to work towards preventing pollution, warming, and rising ocean levels to ensure that plankton continue to do the work nature intended them for, which after all is for a breathing benefit.
Thank you. And now I have the pleasure of introducing our next team, Noah Germolas is a PhD candidate in the MIT Hui Joint Program in Marine Chemistry and Geochemistry. Unfortunately, his partner artist, Heather Stuyvesant, is unable to attend this session this evening. However, we have her on video. Their project is called Visualizing the Unseen.
Hi, so I'm Noah, and I'm a scientist, and one of the things that I think about a lot is chemistry, and specifically, it's the chemistry that microbes employ. You just heard in that last talk about how microbes do a lot for the Earth, and in my view, I come from kind of a school of thought where, realistically, at some base level, they control everything. And so what I do is I focus on the sort of chemicals that they use for life to build cells, to communicate with each other, that they're constantly shooting back and forth at each other. And this happens everywhere on the Earth, including the ocean. And so that gets really abstract really fast because you're talking about basically the language that microbes speak to each other. And Heather decided that she wanted to take that challenge on to try to represent it visually, and she did. But my goal, and both of our goals here, wasn't necessarily to just represent straight chemical data. It was to kind of give an impression of what does a biochemist see when they look at different parts of the ocean. What you see before you in the slide that's on the screen is the oligotrophic, that is nutrient poor, gyre in the middle of the Atlantic Ocean near Bermuda. It's the surface of the ocean. There's very little nitrogen and phosphorus, essential building blocks for cells there. And the organisms there eke out a living in a very minimal way and grow slower than a lot of other places in the oceans. So to me, it's a little bit lonely. It's like a desert. Heather painted an impression of this, and I took some of the chemical data that I have and translated it into music. We don't have time to go through that entire process, but you can hear a little bit of the sample. So if you would hit that button, this is the surface ocean at Bermuda. And that's 1 out of 4 paintings and 1 out of 4 tracks. Thank you.
Thank you, Noah. That was great. Credit to you for writing your music as well. I'm looking forward to seeing more of this. Our next panelists are coming up, and they are Dr. Sujata Murti, who is an assistant professor of atmospheric and environmental sciences at the University of Albany. I believe she was also a graduate of the Hui program. And Marcy Cohen, who's a fine arts photographer. Their project is titled Oceans of Time.
Thank you so much. So I'm Sujata, I'm the scientist, and the photos you're seeing right now are composites that are based off of and inspired by some of my field work. So my research really focuses on using corals from coral reefs to look at past changes in climate and ocean conditions. So the way that works is that corals are awesome and they can grow continuously for centuries at a time, growing into these massive boulder colonies that can be likely as tall as the room you're sitting in, if not taller. And as they grow, they act like little meteorological weather stations of the ocean that record climate and environmental information. So we can look at past changes in this information over the last 300 to 500 years, far beyond what observations or satellite data can tell us. This allows us to better anticipate and predict future climate change in a warming world.
So yeah, I'm Marcy Cohen, I'm the photographer, and as Sujata mentioned, the photographs in this series, Oceans of Time, are composites that include elements from Sujata's dives in the Indian Ocean and Pacific Ocean, I should say Indonesian seas and Pacific Ocean. They're layered in a colorful, dreamlike melody with other images of time and the underwater world. Corals are known for their longevity. An individual coral could grow continuously for hundreds of years at a time, acting as meteorological weather stations in the ocean that record changes in climate and environmental conditions. I photograph the world to understand it, what's right there but unseen, the world under the surface. The chaos of the world is my subject, and my photography is driven by curiosity and the desire to transform the normal order. In the former life, I studied geology and thought about being an environmental engineer. So Sujata's project and the chance to improve our environmental situation were driving forces to getting involved with Synergy and to work with Sujata.
One of the aspects of this program that we were very excited about was to be able to think creatively about how to communicate and visualize ocean and climate research. And so we were thrilled to have the opportunity to work together to think about how to bring people together and inspire them through the universal language of the arts. And so we've started with some of my field work, but we're hoping to continue by looking at the lab work and building on how do we communicate, the broader picture and the implications of this research.
Yeah, I too see a long future for this project. As Sujata's research continues to evolve and bear fruit, I will gain further insight and inspiration that I'm certain will result in the creation of additional work. I recently have spent time with Sujata in the lab at Woods Hole, which was wonderful, and created some new imagery that I hope to use in future composite works. I also plan to have additional in-person meetings with Sujata and photographic shooting sessions in her new lab in the university at Albany State. Art and science generally operate in separate silos. We believe creating more synergy between these disparate disciplines will instill greater understanding, allowing scientists to reach broader audiences and support for their work. We hope our work will also demonstrate the way science can intervene and disrupt the negative environmental forces that lead many to predict a very dark and dystopian future for the planet. We see things differently and have a lot of optimism for the future.
Thank you.
Thank you both. Excellent presentation. Our next team is Dr. Caroline Umenhoffer, Associate Scientist in Physical Oceanography at WHOI, and Dr. Hong Zhu, who is a pharmaceutical professional and an artist. The title of their project is From Sea Salt to Rainfall.
Thanks, Ellen. Good evening, everyone. I'm a climate scientist and oceanographer interested in the water cycle. And that led me to this collaborative project with Hong, From Sea Salt to Rainfall, to showcase the ocean's role in the water cycle. Next. When talking about droughts and floods, rainfall on land, you don't immediately think of the ocean. but you actually should. When considering that 97% of all the water on Earth is in the ocean, if you want to understand anything about rainfall on land, the answer lies in the ocean, because ultimately they are the source of water for any rain that falls on land. Next. As water evaporates from the ocean surface, it forms clouds, and that moisture is then transported onto land. And we're interested in this transfer of moisture from the ocean to land. And we can track this moisture. Next. And that has to do with the simple fact that as water evaporates from the ocean surface, it leaves salt behind. And so prior to a major flood event or a big rainfall event, there must have been some extra evaporation that has happened. And we can track that by tracking the salt content at the ocean surface from satellites. And so as there is more evaporation, more salt is left behind, meaning the ocean surface is getting saltier in that area. And that is what the satellites can measure. Next. And so we can use the ocean's salinity or salt content at the surface as a predictor of what rainfall might be like in another area several months or weeks ahead of time. And that has big benefits to farmers or water resource manager as they are trying to predict and anticipate the weather of the coming months. The whole process is relatively amorphous. It's not something that we can see with the naked eye, this transfer of moisture from ocean to land. And that's where the challenge came in. And Hong has done an amazing job in visualizing this invisible process. Hong, over to you.
Thank you, Caroline.
Next.
Yeah, thank you, Caroline. And I must say, I have felt so fortunate to be part of the Synergy 2 project that combines science with art, which now I have experienced both fields. So I was drawn to Caroline's project as a challenge for myself, both as to create art that is reflecting her study, and also as a challenge for me is to visualize a part of her research that is reflecting the amorphous and invisible ocean salt and the evaporation process. So the short clip you see here is a distilled version of the creation of this art piece. So to do this, I conceptualized and really stared at sea a lot of times and stared at clouds a lot of times. Did a lot of photographs of the sea, the clouds, and the ocean, the heat, which is really the challenging part. So in the end, I thought I'd focus on basic elements. So the water, I used a digital photograph to showcase the ocean and the water, and then use the digital tool to highlight the waves and the flows of the ocean, and also the rise of the moisture in the sky, in the atmosphere. And then later to use also digital tool to put on the crystal to symbolize the salt in the ocean, even though it's not visible, and to give different variation in different parts of the ocean. And then at the end, added the heat, the radiation to combine, to link the process of ocean water becoming the rainfall in the sky, essentially. So with this process is just fascinating and taught me a lot about the process. As I feel personally, creating art and doing research, there's so much in common. We have hypotheses, we conceptualize, and then we use tools, we try it, a lot of trial and error, we experiment, and at some point, with hard work, then it clicks. So that's the result of this project. And I really love it. I love science for its power to discover, to ask questions, to answer questions. And I love art for its power to show the beauty to send messages, to express feelings. Thank you, Caroline, for giving me the opportunity to work with you. And so next, I think week 2 will continue collaboration. I would like to work on her method to actually show the measurement or way to actually look at the salt, which is invisible in the ocean, and to also explore how the project can predict, help rainfall management or stream weather. Yeah. It's been a great learning experience. Thank you.
Thank you both. Wonderful project and very interesting. Our next trio is again, Dr. Caroline Umenhoffer, Associate Scientist in Physical Oceanography at WHOI, Dr. Svenja Ryan, who's a postdoctoral scholar in Physical Oceanography, and Deb Ahrens, who's a lens-based artist. Their project focused on marine heat waves, which is the title of their project.
Working with Caroline and Svenja has pushed my artwork off the wall and into 3 dimensions. Early on in the project, I realized that to convey the scale of the patterns that they seek to find in ever-changing environments, I needed a canvas or a surface that would be able to move like the wind in the water that they study. It needed to be able to move in both predictable and unpredictable ways, and it needed to create patterns that are both simple and complex. I chose to work with fabric because of its dynamic flexibility, and Svenja's animations of the heat waves off the New England coast inspired its final form. This is the story of what's happened to all those kelp beds that have been taken over by sea urchins. And when you look closely, I mean, there's the underlayer is in fact the spines of sea urchins and these sea stars that have moved in, and the Dungeness crab that have been lost, and you know, but I think you can just get lost in also that beauty of the patterns in nature that repeat over and over. I mean, as destructive as these are, they're really beautiful.
And I think we've spoke about it a few times, that these panels nicely convey the message of discovery, and that's what we do in science as well. And you have this big data set and you plot it and you look at it at first and try to grasp like the big features, but then you have to dive in more and more and more, and you find more and more details. And like these panels in the whole, they will give an impression, but you can really go deeper and find these details. And when you come back to educational purposes, kids can look and say, oh, what is this critter? And then, for example, here there's this CTD, which is a typical standard oceanographic instrument, so they can say, oh, what is this? And then you can give more information about how we use it and what you get out of it. And I think, yeah, and even we come here and like, oh, cool, you know, we didn't even see this. And I think that's also even that the print, it'll give you a sense of discovery, because in the beginning I didn't see that Deb implemented the whole map and the ocean currents in there, because you look at it and you see the fish and the code and the critters, but then you look closer and it's again discovery. So I think it even comes out in these prints.
I think it also parallels how we work, as Svenja was saying. I think we so often delve down into the data and we go down a rabbit hole, and it's actually really hard to get out again and, and so on, and to step back and see the bigger picture. And so if this could be done with these panels as well, where you zoom in and then zoom out again, to actually both see the level of detail and the really minute aspects to it, and then also see the bigger picture, I think that would be how scientists work with the data. Artists have approached this, so I think that would be a really powerful message.
Thank you. That was excellent. I'd like to take a moment to remind everyone that you can put your questions for any of the artists or scientists into the Q&A box, which is at the bottom of your screen. Our next team is Dr. Nina Whitney, postdoc researcher at WHOI. Unfortunately, she is unable to attend this evening. Her partner artist is Claire Marshak. Claire is an artist, a designer, a teacher, and a business owner. And the project they've taken on is called Arctica Icelandica.
So when I started this project, I thought it would be fun to combine my skills as a designer and model maker and also my current profession of painting. And I decided what I wanted to do was make a relief sculpture of the clam. And I thought by elevating it to a fine piece of artwork, it would really bring it out of the realm of being just a small little diminutive clam, because you can actually see this particular one is only about 3 inches, but it is very, has so much information in it. So having decided that's what I was going to do, I had to come up with a process where I could actually do model making in my painting studio, since I don't have a regular model shop. So I decided to build it out of foam core. So I had to start with layers and layers of foam core, and that's where I realized, I've learned this from the past, I did a lot of preliminary work, and I actually did a scale model, because you learn a lot by doing the technique, and I also experimented with the painting process, and it's a lot easier to make mistakes when you're working small rather than large. One of the things about how I started was I actually did a schematic drawing, and this kind of gave me some information about what I thought, how big I thought it would be, and how it was going to get assembled, the whole final process. And I really enjoy this part of designing. I was almost designing a product. I also did a lot of sketching in my sketchbook with some of the other project I'm going to do, which is the timeline. And I was just trying to figure out some of the graphics, and this I enjoy. This is a lot of fun.
Doing research on clams is a little bit like uncovering a puzzle or a hidden message in the shell. So we break them open. It's usually really hard to tell how old they are, so that's probably the first exciting thing, is to figure out, is it 100 years or is it 500 years? There's a champagne bottle sitting somewhere for whoever finds a clam that's older than 507 years. So that's the first thing, to just figure out how old these guys are. But then we essentially use a drill and sample each one of those layers and analyze that, and that all takes a while. And then you get to plot that up and see what happened. What was the temperature in the ocean in 1730 or 1620? And so that's pretty exciting to just uncover what these clams can tell us. And I think my big aha moment was during my PhD in the Gulf of Maine, which is where I originally did my research. The Gulf of Maine is warming faster than 99% of the rest of the world's oceans, so it's warming very quickly, but we only have a temperature record that goes back to about 1900. And that temperature record says that the Gulf of Maine is pretty much, more or less, been warming since 1900. And so when I plotted up my isotopes from that region, I realized that that record went in at almost the coldest point in the Gulf of Maine in the last 350 years or so. which was pretty interesting to get that perspective. I think if you just look at the temperature record, you maybe assumed that the Gulf of Maine was more or less stable and then started to warm at the start of the Industrial Revolution. But in fact, it's been cooling for almost 1,000 years, according to the modeling that we've done. And only recently has that trend reversed and it started to warm again with climate change. So that was pretty interesting to just uncover that puzzle.
Thank you, Claire and Nina. Our next team is Jing He, a PhD candidate in the Hui Joint Program. Unfortunately, she was unable to attend this evening, but her partner, Janine Wang, will be here. Janine is an artist, an architect, and a professor at the UMass Dartmouth campus. The project they've called Submesocol Soup, and I'm sorry, I'm butchering that name. You will hear about shortly.
I'm Janine Wang, the artist in the artist scientist team. I'm Janine Wang, the artist in the artist scientist team. I would like to share our project, Submesoscale Soup, a poetic typology of ocean physics. This artist book, Submesoscale Soup, presents an artistic response to physical oceanographic phenomena and is a collaboration between myself and scientist Jing He. Inspired by the scientific illustration books from the turn of the century, our goal is to make science beautiful and accessible to a wide audience. However, unlike the books that inspired us, the science we explore that is not easily seen by the average person. This is due either to the large scale of the ocean currents or the processes hidden deep below the ocean's surface. Our book collaboration aims to visualize unseen beauty of ocean physics. Oceans cover 70% of the surface of our planet and play a crucial role in the Earth's climate system and, consequently, our lives. How the ocean moves is a critical component of how it does its job, regulating global temperatures, taking up carbon dioxide from the atmosphere, and supporting marine life. There are many different physical processes that occur simultaneously, which gives rise to countless types of currents and movements at different scales. It is through the years of developing sophisticated instruments and making careful observations of the ocean, using math to describe ocean dynamics, and writing code to simulate it on the computers, that scientists have been able to untangle and understand the different components that make up ocean circulation. In our book, we showcase some of the ingredients and processes that go into creating the, quote, submesoscale soup, a particular type of ocean dynamics that is the focus of Jing He's current research. The submesoscale describes motions of intermediate size in the ocean with lengths of 0.1 to 10 kilometers. These currents spin as fast or faster than the Earth's rotation, and they are a challenge to see because they are too small to be observed from satellites, but too large to be seen from a ship in the ocean. Furthermore, these currents are often described as, quote, soup, which is an apt metaphor, just as how good a soup with complex flavor is made up of combinations of ingredients. Heating and cooling the ocean's submesoscale soup is also a rich blend of different components and mechanisms. To study these currents, Jing virtually recreates them on computers by following a general recipe, but like most chefs, she modifies the recipe to get different flavors and varieties. After hours of conversation with scientist Jing He and study of her research on ocean currents, I set out to produce a body of work with images that evoke her findings through pattern, color, and texture. Employing the centuries-old process of marbling, I suspend paint in a tank filled with Carrageenan solution to form fluid patterns that can be transferred to paper. Carrageenan, coincidentally, is made up from seaweed, forming a fundamental connection between artistic method and my subject. The marbling tank therefore simulates a miniature ocean in which to manipulate paint to create patterns that suggest various ocean current movements. The book shows diptychs or pairs for comparison to highlight concepts. I will quickly move through the remaining 10 pages. In the book, each concept is introduced, titled, and captioned. Upwelling, front. Bloom and phytoplankton diversity. Multiscale. High turbulence and low turbulence. That's it. Thank you for listening. We will post our book on the Synergy website for you to view and read.
Thank you, Janine. Our next team is Dr. Larry Pratt, Senior Scientist at WHOI and instructor in the MIT Joint Program, and Ellen Beagert, who's an artist and a landscape architect, and the project they've called Turbulence.
Well, Ellen is unable to be here tonight, but you will hear from here on video. Yes, we've been talking about turbulence a lot, and I'm sure you've all experienced turbulence, probably flying over the Rocky Mountains. But the ocean, as you just heard from the last presentation, is also filled with turbulence. And the turbulence is generated by different mechanisms. It can be due to the instability of currents at the surface, as you see in the right-hand picture, breaking waves at the surface, and then things like the water sloshing back and forth over the rough bottom topography. And you might well imagine that the complexity that's generated by turbulence makes environmental prediction very difficult. And so, in fact, understanding turbulence is one of the most difficult and most important problems in classical physics, and one that some people have spent their whole careers looking at. So Ellen and I have spent a lot of time talking about this, the fact that turbulence is very non-homogeneous. So it differs in character and in intensity from one part of the ocean to another part. And so why don't we hear from her and what her artistic vision is of this.
Hi, my name is Ellen Beagert. I'm an artist and a landscape architect, and I've been working with Larry Pratt on the Synergy 2 project. The focus of our project is turbulence. We've been talking about it at the global scale with the general circulation down to deep turbulent passages to micro actions that add up to larger movements. So far, the process has been discussing, digesting ideas, bouncing thoughts, and finding a way to interpret these motions so that others can connect with ocean research in a new way. The project has 3 components. The first one looks at the massive water below the surface of the ocean and the slow, calm impression it has compared to the layers above and below it. We started this out by taking material and discussions that I had with Larry, trying out smaller areas to get an idea of layout and drawing out texture and patterns to see what would get the idea of moving water across. The other 2 components are still being worked on. One uses a buoyancy sphere to interpret global water circulation by etching in patterns that connect up to make the larger system. This sphere was used to collect data in the deep ocean and has the scars and droplets to prove it. The other uses Larry's light photography talent to interpret movements of water and how tiny turbulent actions can add up to make it. This project has given me a glimpse at the complexity of moving water in our oceans and a peek at how a physical oceanographer sees and understands it. I'm grateful to be able to dive into this turbulent system and to share this interpretation.
Well, I think you can all see what draws me to Ellen's work. It's beautiful, it's figurative, it gives me sort of a whimsical view of the environment, and it's made me look at the ocean through a really different lens. So thank you, Ellen.
Thank you, Larry and Ellen. So our last team is about to come up, and I just want to remind you again to please put your questions in the Q&A box at the bottom of your screen. I'd like to introduce Dr. Susie Clark, graduate of MIT Hui Joint Program and currently a postdoctoral associate at the University of Minnesota, and her partner, Keith Prue, who is a freelance photographer and business owner. And the title of their project is Bloom.
So hi, everyone. My name is Susie, and I'm the scientist in this partnership. And Sarah, you could switch to the next slide, please. So the piece Bloom was actually inspired by a natural phenomenon that we call harmful algal blooms. You might better know these as red tides, which is kind of the more common name for them. And this is an aerial image showing what a red tide can look like. It can really turn the water that red. That's not Photoshop. And red tides can be viewed from the macro scale, like this picture, or they can be viewed from the micro scale. So the image on the left of these three panels is a drawing that shows individual cells. Typically, we think of algae as giant seaweed that washes up on the shore and wraps around our ankles, but there are also things called microalgae. These ones are very, very small, and they can only be seen with a microscope. The ones that I study are 10 times narrower than the width of a human hair. So why do we care about something that's that small? How can it possibly affect our lives when all you can do is see it under a microscope? Well, one cell isn't typically a problem, but when they grow really fast, there are so many of them that tens of thousands can fit into a bottle of water. And that's what we call a bloom. Some of these algae can be toxic, and when filter feeders such as shellfish eat them, the shellfish then become toxic. Then if those toxic shellfish make their way onto our plates, it can make us sick, as shown here in this cartoon. The metaphor that I like to use to understanding blooms, oh, sorry, could you go back a slide, please? Thank you. So my research involved trying to figure out what makes these cells bloom. And the metaphor I like to use is, imagine someone gave you a big bowl of soup and you have to try to back out the recipe, not knowing what the chef did. You have an idea that you might need some vegetables and some salt and that you should mix it and then you should heat it, but you don't know exactly how the soup was made. So trying to understand an algal bloom is a lot like that. We have an idea of what the algae need to survive, but we don't know exactly what the conditions were to make them bloom. Sometimes they can be caused by nutrients running off from agriculture or by changing ocean temperatures, or they can be transported to a new place by ship ballast water. So to figure out what causes blooms, I used a combination of computer models and data collected from samples of ocean water as clues. And when I was working with Keith, I tried hard to explain this aspect of my research, the way these blooms can be studied from a variety of scales, the way they can be both beautiful and dangerous, and the way I looked for patterns in a confusing tangle of data.
Hello, I'm Keith. I wanted to incorporate the main attributes of the blooms, namely their unpredictability, the randomness, the complexity, their multifaceted nature, mystery, repetition, yet the diversity and their beauty. The tension between the beauty and the danger of the blooms was a constant theme with the discussion with Susie, and the attempt to capture that dynamic of the individually harmless but collectively dangerous cells. Blooms are visible from afar, even from space, yet the cells, as Susie explained, are microscopic in nature. We looked how blooms appear vertically in the water strata and not just on the surface. This was compared to how a painting has the dimensionality created from multiple brushstrokes, yet one sees the overall picture, not the individual components. The original concept of the piece was with reference to Chuck Close's mosaic imagery, which reached differently depending on the viewing distance. From a research perspective, Susie does not visualize blooms at the microscopic level, but en masse at the Gulf of Maine level. When conceptualizing the piece, I wanted to capture the essence of her work, not the exactness. To this end, the piece includes false colors, that is, colors that are not present in blooms in nature, and uses abstract concepts rather than the factual thing itself. I took pictures of Thunderhole in Acadian National Park in Maine. The original arrangement is 16 squares, 8 with original colors and 8 with false colors. The final version of 400 squares is arranged by chance, influenced by the work of Ellsworth Kelly. The final piece has the intended 3D dimensionality, and the straight lines ebb and flow, reflecting the natural movement of the ocean due to a visual phenomenon known as cafe wall illusion.
And the key messages that we hope that people take away from this piece are, one, the obvious complexity of this problem that we're addressing. It's showcased very well in this piece that Keith created. And also, from my perspective, what motivates me is that the ocean is beautiful and interesting, but it also is deserving of respect because it can have a direct impact on our lives. So thank you.
Thank you, Keith and Dr. Clark. And now we will turn over our session to Jennifer Kenyon, who will moderate the Q&A for our panel of artists and scientists.
Thanks, Ellen, and thanks to all of the artists and scientists who participated in this program. It was a pleasure seeing so many of your cool artworks, and it's so exciting. We are a little short on time, so we'll keep this Q&A session pretty short before we wrap up. Our first question is for Noah from KDH. I have a few questions for Noah. You said that we heard the Service Oceanette Bats. For those of you who don't know, that's the Bermuda Atlantic Time Series site. That's a study site in the Atlantic Ocean, which was one of your 4 musical pieces that you prepared. Which sample locations and depths are behind your other 3 pieces? Are they musically distinct in any particularly interesting ways?
Yeah, one of the main focuses of the whole piece is that each of these ocean regions that we're doing is distinct. And the surprising thing is that some of them are very close to each other. So Bermuda is in the middle of the Atlantic Ocean. It's in the middle of this gyre where the surface currents kind of circle around and bring water in slowly, and nutrients are very depleted. But a lot of the ocean is locked in these gyres, something like 1/3 of it. And so what this is for oceanographers is basically what a really good representation of what the ocean is kind of at steady state. So people study it really heavily, hence the Bermuda Atlantic Time Series site, where a lot of scientific data has been collected. The pieces that I've composed and the paintings that Heather has painted come from samples taken in my own backyard in Vineyard Sound, as well as 3 different depths at Bermuda. One right at the surface where the sunlight is harsh, the water is a crystal blue, and it's a hard knock life for the microbes there. The next one is from the chlorophyll maximum, which is a little bit deeper, where the intersection of nutrients coming up from below and sunlight coming up from above make this giant microbial party. And that's about the busiest it gets around there. And then the last one is from the deeper part, the part where the light doesn't reach. It's the Mesopelagic, in other words. Life is a lot slower there. It's dark. Things are basically living off of whatever rains down from above. And so you could imagine them as kind of, whereas this top was the desert, basically the chlorophyll maximum is the jazz, it's the party. And the deep part is kind of a spacey, episodic, sad kind of dirge almost.
Thanks, Noah. That was really beautiful and a great answer to a complex question. The next question is from William L. It's actually for me and Lori, so maybe Lori, I'll let you answer this one. It's, can you talk about the experience of condensing your research and writing in storybook form for young people? You have to unmute yourself, Lori. All right, well, while Lori figures out how to unmute herself, I'll jump in to say that it was actually really difficult. The first run, I think I wrote like 20 pages of science, and Lori basically was like, that is a non-starter. And we had to parse it down, and it actually, so I study marine radioactivity, so it's kind of a hard thing to explain to people a lot of the time. And it was great working with Lori because she actually had no background in that. So I had to really think about how to communicate my science in a way that was much more parsed down than I had originally intended. I see Lori's unmuted now, so maybe she can give some insight.
Sorry about that. Yes, and I was probably a good stand-in for the 10-year-old. That was our target audience. It was a constant back and forth because she would write something and I would get some new imagery from it, and that would take me on a different path, and then she would look at the images and maybe rewrite something that she had already rewritten. So it was constant back and forth, and it was very challenging, and it was a terrific experience. So.
Yeah, and I have to say, I loved working with Lori, and I'm sure all of the artists and scientists would say something similar about their collaboration. With that, we are over time, and I know everyone is eager to get on with their evening, so I will turn it over to Ellen for our closing remarks, and I just want to thank everyone who came. It was such an exciting time.
So our program is about to conclude, and thank you for all being here. Before signing off, though, I'd like to take a moment to thank our presenters, our guest speaker, and those who attended tonight's program for your contributions to this event. I'd also like to acknowledge the contributions and support of our sponsors, the MIT Woods Hole Joint Program in Oceanography and Applied Ocean Science and Engineering, the Center for Marine and Environmental Radioactivity, the Mass Cultural Council, the MIT Office of Graduate Education, and the Council for the Arts at MIT. Thank you again, and enjoy your evening.